Welcome back to Applied Algebra and Trigonometry. Today we're going to combine two sections from your textbook, Rectangular Coordinates and Function Graphing. This video is the first of two. Here we have two number lines or axes oriented perpendicular to each other, forming a Cartesian plane. Let's just do a little bit of review about the Cartesian plane. We consider the upper right quadrant to be the first quadrant, the upper left to be the second, and we go around numbering in a counterclockwise direction. If you examine the x coordinates, which is what we usually call this, so let me go ahead and label that as x, although it could be another variable, as we've already talked about. Anyways, the horizontal axis is the axis of the independent variable, and the vertical axis is the axis of the dependent variable. I will go ahead and label that y, although if you remember, you could use function notation here. It could also be labeled f of x, the function of x, because its value depends upon the independent variable. If you examine the plane closely, you will see that moving from the right, from the origin, which is the point where the two axes intersect, you'll see that the x values are positive and increasing if we move to the right, and the y values are positive and increasing if we move vertically. Every point within that first quadrant will have an x value, in this case 6, and we always list the independent variable first, so 6, and the dependent variable, or the y value, which in this case is 2, is listed in the second position in our coordinate pair, and they are always enclosed in parentheses. This should be review for you, but we'll do it just to make sure everybody's on the same page. In the first quadrant, every x value is greater than 0, and every y value is greater than 0. Another way you can indicate that is to say all the x's are positive and all the y's are positive. In the second quadrant, when you take a look at it, the x values are becoming more and more negative as you go to the left from the origin. The y values are positive. So in this quadrant, we have x is less than 0, but y is still greater than 0. In other words, x is always negative and y is always positive. In the third quadrant, we are still looking at x as being negative, but now the y values are negative as well. And we can rewrite that in that fashion. Both the x and the y are negative. In quadrant 4, we have positive x's again, but we still have negative y's. So we could write that as plus comma minus positive x negative y in the fourth quadrant. Once we have agreed on how this coordinate system works, we can now label any points, and we would all label them consistently. The x value for this point is -2, the y value is 5. The x value for the second point that I've drawn here is 6. The y value is 0. It is right on the x-axis. Okay? It is not above or below the x-axis. The y value is just 0. Likewise, if I listed some coordinate points, you could tell me where these are located. So -3, 1, 2, 3, -3 in the x direction, +2 in the y direction. And it's always a good idea to label your points so you are very clear to yourself and to whoever is reading your information as to what you have done. And -5, -5, that would be 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. If I were to tell you that I wanted to draw a rectangle on this coordinate plane, this Cartesian plane, and I had those 3 points already chosen for parts of my rectangle. So there's 3, 2, there's 3, -1, and -2, -1. Where would you tell me that the last point needed to be? I hope you would assume that you could just draw the rectangle, because you could, and there would be the point at -2, 2. Notice if I put that at -2, 2, okay, these aren't in the order they are on the plane, but here's 3, 2, and right below that with the same x value is 3, -1. To the left of that, with a different x value but the same y value, is -2, -1. Above that, the same x value and the same y value as our first point is the last point on our rectangle. A quick note here. Yes, you can have decimal values or fractional values for your x and y coordinates. This would be at 1.5 for our x and -3/4 for our y value. 1.5, -3/4 would be approximately there. We can also determine the distance between any 2 points. First, we have to determine what these points are that I've drawn here. Let's see, that's 6, 7, and 2, 4. So we want to know the distance between them. So what is that distance? Well, we can figure out that distance by dropping a vertical line down this way and a horizontal line across that way. And those two lines will cross right here at a point that has the same x value as the higher point and the same y value as the point to the left there. So the point 6, 4, and look at what we formed. We have formed a right triangle. Okay, whenever you have a right triangle, you know that you can use the Pythagorean theorem. C² = A² + B², where A and B are sides of a right triangle, and C is the hypotenuse. If we want to find the length of that hypotenuse, we need to take the square root of the quantity A² + B². How do we find A and B, though? Well, A will be the distance in the x direction between those 2 points. So we can say 6 - 2 will give us that distance, and then we square it. Then we take 7 - 4, the y's of the points, the y values of the points to the right. So that is actually 4, which we're going to square, and 3, which we're going to square. And that will give us the square root of 16 + 9, or the square root of 25. Now, we are solving this, right? So normally we would consider, because this is a part of the solution, the positive or the negative square root of 25, which would be 5. However, we are looking at a distance, and distance is never negative. It is always positive. So our distance here is 5. Okay? And in fact, if we write that as a formula, we can say that C, which is equal to x2, x value of the second coordinate minus the x value of the first coordinate squared, plus the y value of the second coordinate minus the y value of the first coordinate squared, will give us the length of the hypotenuse, which is also the distance between any 2 points. Now, this worked out as a nice integer right here. It will not always work out so, but we have not yet studied what we do with radicals, how we deal with them, the various laws of radicals and exponents and all the stuff we're going to get into. So I gave you just a simple one right here. Square root of 25 is 5. Later on, you will be able to deal with anything you come across without referring to your calculator. Although it will be a useful tool, and I will be teaching you how to use it as well. So So let's say we are given the point -4, 1. And then we are further asked to locate Q, a point Q, such that PQ is bisected by the origin. So we are going to extend a line from -4, 1 through the origin and out to the other side to some point that is just as far away from the origin as -4, 1 is from the origin. But just how far away is P from the origin? Let's use our distance formula to determine that. So C equals the x value, -4, minus, remember the origin's coordinates are 0, 0. So -4 minus 0 squared plus 1 minus 0 squared will give us the distance from point P to the origin. Square root of -4 squared plus 1 squared. Well, -4 is just 16 when you square it, plus 1, or square root of 17. Now, this is one way we could do it. We could measure out 17 units along this line, and then continue another 17, and find our point. But I would argue there's a better way to do that. So let's move this out of the way as well. And let's look at what we did, in effect, when we subtracted 0 here from 4 here, and we subtracted 0 from 1. We went 4 in this direction and 1 in that direction. 1 in the y direction, 4 in the x direction. In fact, we went down 1 and over 4. If we continue that slope and go down 1 and over 4, we will wind up right there. The distance from -4, 1, and the distance here, which is to the point +4, -1. Both of these distances are equal to the square root of 17, which is what we found with the distance formula. We didn't specifically need the distance. We could use the slope to locate point Q, which is exactly what we were asked to do. Now we're going to play a little game called Where Are the Points? Where are the points where y equals 2? Well, any place where y equals 2, no matter where you want to put that, except it's not a dotted line. It's every integer, every fraction, every irrational number to infinity, from negative infinity to positive infinity, where y is equal to 2. Okay, so it's the line y equals 2. It's a line 2 units above the x-axis and parallel to the x-axis. All right, next question. Where are the points where y equals x? Let me do this in a different color. Y equals x. Okay, well, at 0, 0, y equals x. At 1, 0, y equals x. At -4, -4, y equals x at all of those points. And, in fact, everywhere along an infinite line, 45 degrees from the x and y axes, runs through quadrant 1 and quadrant 2. Let's try another one. Let's look at where are the points where x is less than -3. Well, let's find out where -3 is on the x-axis. 1, 2, 3, it's right here. But it cannot equal, x cannot equal -3. So we make it a dotted line to say it's infinitely close to this, but it never touches -3. And which values are less than that? Well, one way to be sure, if you're not quite sure, is to pick a point on one side or the other. And I tell you what, 0, 0 is a wonderful point to pick because zeros are easy to put into any formula. So if we choose the point 0, 0, and we put 0 in there, because the x-coordinate of 0, 0 is 0, is that true? Is 0 less than negative 3? No, it is not true. X is not less than negative 3 to the right of that green line. However, to the left of that green line, yes, x is less than negative 3. So that's how we would graph x is less than negative 3. That is a dotted line. Let's look at one more situation. Where are the points where their y values are greater than or equal to 5? Because it says or equal to, we actually go ahead and draw a line where y equals 5, and it is all points, all integers, all fractions, all decimals, all irrational numbers for the x value. For the y value, it always equals 5, and it's a little bit sloppy there. I'm sorry about that on the right. But those points include the points on the line y equals 5 and anything above them. You want to check the origin. The y value of the origin is 0. Is that greater than or equal to 5? No. So we shade the opposite side of the line. Now, the point 0, 5 satisfies that inequality. 5 is greater than or equal to, it is equal to 5. And the point, so 0, 5 is 1. It's an example. And the point 2, 6.5 is an example. You could cite an infinite number of points that would be in this region. 2, 6.5 is one of them. Notice that all of the points above the line y equals 5 and at the same time to the left of x equals negative 3 are included in this area, which stretches infinitely in the positive y direction and infinitely in the negative x direction. All of those points satisfy both of those conditions. Their x-coordinate is less than 3, and their y-coordinate is greater than or equal to 5. Please read your textbook, familiarize yourself with rectangular coordinates, and look for part B of this video. We are not done yet.